Welcome to our periodic trends video, last one in the atomic structure unit. I just created just a little bit of a helpful diagram to myself. This is the kind of thing that you might want to sketch really quickly as soon as you get your test paper, just so that you don't have to be worried about it, thinking about it 45 minutes into the test. So as soon as you get your test paper, jot this on the back or something and then start in on the test. So another thing to consider with periodic trends, not only is it atomic radius and ionic radius, but also ionization energy and electronegativity are the factors. So we want to be thinking about nuclear charge. And what does that mean? That means how many protons are there? What's the pull like? And so that's going to be one factor in assessing the trends. Distance or shell. The shells. So how many energy levels away from this nucleus are we? What's the distance looking like? And then what kind of, how many electrons are there in between the protons in the nucleus and these outermost electrons, the valence electrons? Could there be some shielding at play where some of the inner electrons actually prevent the protons from having as much of a grab or as much nuclear force on the outermost electrons? So I'd like to just compare 4 elements. Beryllium at number 4, oxygen at 8, radium at 88, and livermorium at 116. If you have a really old periodic table, they might have like UUM or something like that. But this is one of the newer elements that have been named, and I wish there was a really good story, but it's just the name of a town where a lot of folks that work on heavy elements work. So, but it's a cool name, livermorium. So we'll use that to compare. And I did intentionally pick elements that are in the same groups and in the same period. So if we're going to compare across a period, which one has the largest atomic radius, beryllium or oxygen? We also want to pick up one of the factors as like our support as to why we might pick one or the other. So looking at beryllium, looking at oxygen, as we go sort of across the period, we're not increasing distance. We're not increasing any kind of shielding. The distance is the same across the period. All that's happening is the nuclear charge is increasing because we're adding more protons as we go across, which the protons will help to sort of squeeze that those electrons closer to it. So further on the left-hand side of your periodic table will be the area where the protons will have the least nuclear charge. So beryllium will be the largest, whereas with oxygen, it's the same distance, but there's more protons pulling those outermost electrons in. Comparing beryllium and radium, here we've got definitely like increased distance. There's more shells that are in play. There's tons of electrons in between shielding. Please refer to the periodic tables, really good, or the PowerPoint, I should say, because there's some really good illustrations and animations there that show the shielding effect. So in terms of ionic radius, if we're going to compare two anions, so the oxygen ion and the livermorium ion, which would have the largest ionic radius, the livermorium ion would, again, for the same reasons that radium does. There's more distance, there's more shells at play. There's going to be some more shielding happening here. There's more protons, but they're further away from the nucleus, and there's going to be electrons in the way, doing some shielding. In terms of the largest ionic radius between radium and beryllium, it would also be a radium. So following the cations, it also increases going down. So electronegativity is basically referring to the affinity that the element has for an electron. What kind of pull does it have? Does it want to, let's say, rip an electron off of another bypassing atom? Who has the greatest affinity for electrons, beryllium or oxygen? Quite frankly, beryllium does not even want any, it does not want to gain electrons. Oxygen definitely wants to gain. It wants 2 more electrons, then it becomes looking like a noble gas. So beryllium's got no business with trying to gain electrons. So oxygen's definitely got the higher affinity. So between beryllium and radium, you would say neither one have very high, but we've got to pick one over the other. So if anybody, it would be beryllium, because beryllium has less distance, less shielding. There's a greater nuclear charge because there's less distance that the protons have to play. So they might, if they ever wanted to gain an electron, it would be easier for beryllium to do that. Ionization energy is the energy required to remove one electron. And so we can have first, second, third. So here we're going to be just speaking to the first ionization energy. How much does it cost in terms of energy to remove one electron from livermorium or from oxygen? And so who has the highest? Livermorium, although it does not want to give up any electrons, those protons are working over a greater distance. There's lots of shielding. There's definitely ways to remove electrons from here easier than oxygen. Oxygen, those electrons are very close to the nucleus. There's a really strong nuclear charge. You will need a very high amount of ionization energy to remove those electrons. In fact, fluorine is the element with the highest, and that's just right next door. Between radium and livermorium, comparison of the ionization energies. If we go across a period, the element with the highest is going to be more to the right side. So the highest ionization energy is actually going to be livermorium, as opposed to radium. And the reason being is that as you go across a period, you add more protons, but you don't add distance. So, you don't increase the shielding. All you do is just add more pull into the center. So technically the atomic radius is also going to be smaller for livermorium, and the nucleus will have a greater pull. So speaking of ionization energies, I'd like to just take one quick peek at first, second, third, and fourth ionization energies. So here we have in kilojoules the energy required to remove one electron from this mystery element. So the first electron gets removed at 738 kilojoules. A second electron gets removed at 1,450 kilojoules. A third electron gets removed at 7,730, and then the fourth at 11,000. So the question is do we think this could be sodium, magnesium, aluminum, or silicon? So the difference between all of these, this has 1 valence electron, 2 valence, 3 valence, and 4 valence electrons. Our strategy here is to try to see the jump, let's see a spot where there's a significant increase in the energy required. So I would say, to go from here to here, and you can actually take this number big number divided by small number to see how many times, but it's approximately 2 times jump. From 1400 to 7700, here we're looking at, what is that, about 4 times jump, 5 times jump. And then from here to here, we're not even at 2 times, so it's about like 1.5 times jump. So looking at this and saying, okay, this is obviously the big jump. The jump is from 2 to 3. And what does that mean? So it's like, I think it's a good idea to kind of draw the line. It means that these are our valence electrons, and that this is in a lower energy level or shell. So if we were to draw out sort of a Bohr diagram, we can imagine these 2 electrons being in the outermost shell, and that this guy might have been one of the ones from the inner energy level, the one that's stable already. So you can remove these first 2 easily. But if you want a third one, if you want this one, it's going to cost you. It'll cost you 5 times as much energy as you spent on getting these guys. So for this, we would say this is probably magnesium. Why? Because it's showing 2 valence electrons.